The construction industry undoubtedly is one of the key contributors setting in motion an unprecedented global environmental crisis. 60% of the buildings and 25% of the infrastructure on Earth by 2050 still yet must be built. The building sector, widely dominated by reinforced concrete constructions, is responsible for 40% of the global energy and process-related CO2 emissions. Decarbonization of the building sector is critical in meeting the 1.5 degrees Celsius Paris target, but emissions associated with the sector reached an all-time high of 10 gigatons CO2 in 2019. Cement production alone accounts for 8% of all global emissions caused by humans, and the same applies to steel production. Thus, by 2030, embodied carbon emissions from all building activities will need to be reduced by 40% according to recent calculations. If everyone on the planet consumed as much as the average US citizen, 4 Earths would be needed to sustain their lifestyle and energy consumption. The question arises, what actions we as builders can explore to foster a more sustainable construction process for the immediate future. Our line of inquiry focuses on a specific type of architectural space that can be found throughout most of the world, the office space. Usually, the layout is designed on a repetitive two-dimensional grid, which is followed by a 3D evolvement of the building. A fully glazed post-beam facade structure is still a preferred design choice, even though the caused environmental effects on the indoor climate present many challenges. Evaluating the embodied carbon for each isolated building subcomponent highlights that the slab construction alone contributes about half of the total embodied carbon and material usage. This finding only targets the raw structural construction. We therefore zoom into a subunit of the building. Reinforced concrete slabs require an extensive usage of formwork and steel reinforcement before the concrete itself is poured on site, whereby almost half of the costs and labor efforts can be found for the installation and assembly of the formwork. Additive manufacturing could be used to create zero-waste and highly customizable formworks with the potential to further reduce the overall usage of reinforcement and in-situ concrete. In office buildings, a common strategy is to install an elevated floor. Mechanical, electric, and plumbing units are usually installed on the ceiling, regulating, for example, the mechanical ventilation. This form of ventilation, in conjunction with noise disturbance by the inhabitants, result in the installation of retrofitted acoustic ceilings. The installation of the facade with further connection detailing completes the assembly. We end up with a total construction package ranging between 50 to 80 centimeters. The aim of this project is to reduce the slab's material consumption by at least 50% and to integrate functional layers only by the means of geometric manipulation, hereby minimizing the overall slab package. Ceiling constructions always have been a canvas for artistic expression, but also displayed the ingenuity of the current status quo in engineering. In a study, current slab construction systems were analyzed. Although all systems have potential to be optimized for the stated application, 2 systems, the cap ceiling and the buffle slab structure, seem especially promising. Studies showed that the systems already offer great potential based on a life cycle assessment of reducing embodied carbon, but also offer, for example, good sound absorption qualities. The project Kappe Plus aims to revitalize cap ceiling constructions. A hybrid system of wooden twin beams and assembly of reused, but also function-integrated additive manufactured bricks were explored. Due to the diminishing of skilled craftsmanship capable to build cap structures, an exemplary robotic fabrication hub was realized to evaluate the feasibility and automation potential for such structures. Cap ceilings span in one direction. The project Kassette Plus explores a 2-directional tension structure, a 2-way joist slab. This system deploys an array of additional synthetic formwork bodies that are cast out once the on-site concreting is finished, hereby creating voids resulting in material savings. The issue with the system is that those formwork bodies are only reusable a certain amount of times and need to be disassembled later, even amplifying the costs and labor efforts in the construction period. Pierluigi Navi explored alternative form-finding methods following the principal bending moments to foster a more optimal geometric articulation of the rib structure. An algorithmic process was designed by our team to analyze and generate such form-found patterns. As mentioned, the problem is that such customized plastic formwork bodies are very expensive to produce. Large-scale additive manufacturing could solve this shortcoming. An automated, algorithmic, and digital process was created to design and fabricate the customized formwork bodies. We start with the vertical extrusion of the side walls, which can be shaped depending on further aesthetic or performative qualities. The slicing process defines the attributes of each printed layer, and additional algorithms can evaluate and adjust overhang conditions or optimize the structural integrity of the freshly printed material to ensure its printability. A custom print path generator enables to further generate the machine code for the physical prototyping. With this process, highly customized geometries with surface detailing below sub-centimeter level accuracy can be produced quickly and with ease. Such objects are usually referred to as lost formwork, but unlike other systems, these 3D printed geometries stay as permanent or zero-waste formwork in the final construction. This allows to explore additional small-scale geometric form finding to integrate thermal and acoustic properties. Thermal active building systems use heating and cooling pipe networks that are embedded into, for example, the ceiling. By creating a larger surface area and reducing the volumetric mass via the formwork bodies, the heat transfer can be regulated more dynamically. But retrofitted acoustic ceilings would diminish the effect of such slab-bound systems. So therefore, a novel process was evaluated and tested to calibrate the sound absorption by further geometric detailing of the formwork bodies. An algorithmic process was programmed to create highly customizable Helmholtz-resonators. These are void cavities that act as sound absorbers and can convert sound energy into heat as sound waves within the various frequency bands accelerate a small air mass in the neck of the resonator against a larger body cavity acting as a spring. Depending on the volume of both the bottle neck and the bottle body, various frequencies can be absorbed. These cavities can also be arrayed to a compound linear absorber. Various geometric attributes of the resonator were modified with the goal of increasing absorption at resonance and increasing the bandwidth of the effective absorption range. The algorithmic model was imported directly into the multi-physics simulation environment, COMSOL. The incident and scatter pressure fields were simulated, from which the surface normal absorption coefficients were calculated. Subsequently, the numeric model were compared to a set of 3D concrete printed physical twin models which were tested in an impedance tube. This process showed that the numerical and empirical results had a high degree of overlap, proving that the formwork bodies could individually or as a cluster be precisely calibrated to act as sound absorbers just by the means of geometric form finding. A custom algorithm was designed to integrate such resonator cavities into the print path generation. Various parameters controlling the shape of each cavity, but also again as a combined spatial system, can be instantiated for the necessary acoustic threshold values, for example, absorption, diffusion, reverberation, and scattering, while ensuring conformity with DIN standards. By simulating the printing process, including cement hydration, curing, and autogenous shrinkage, the usage of CAD and CAM software can offer more complex design features. Previous research pointed out that the printing speed optimization is crucial to find a balance between buildability and interlayer adhesion, both of which are strongly dependent on the waiting time of layer-on-layer deposition. Our custom manufacturing process allows to control these parameters, which could massively help workers on-site to use on-site fabrication hubs to detect any small deviation in the ongoing construction work and use the accessibility of the design features to locally alter the individual geometry, enabling the overall element to fit more precisely in the actual environment. The custom workflow proved to be very robust, as all of the 36 individual formwork bodies for the demonstrator could be built within 1 day without errors. Due to their low weight, the printed modules can be easily managed by 1 or 2 workers. To further streamline the montage sequence, all formwork bodies were tagged with Aruko markers containing information such as the individual position of the piece and the final construction and their weight. Regardless of their current position, each formwork can thus be identified via the associated marker and accurately positioned through holographic instructions. Currently, a catalog of construction systems and formwork geometries is being generated. Applications ranging between renovation and future construction projects. Overall, this first research stage could successfully prove that the usage of multifunctional formwork bodies can result in a massive reduction of the deployed resources for slab constructions. Additionally, only by the means of geometric form finding, linked with state-of-the-art digital analysis processes, properties such as sound absorption and thermal exchange can be integrated into the articulation of the formwork, making retrofitted functional layers obsolete.